Chain of events, cause and effect. We analyse what went right and what went wrong as we discover that many outcomes can be predicted, planned for, and even prevented. I'm John Chidgey, and this is Causality. Causality is part of the Engineered Network. To support our shows, including this one, head over to our Patreon page. And for other great shows, visit engineered.network today. Challenger, the Space Shuttle. My first memory about the Space Shuttle was when I watched a 007 movie called Moonraker. It was released in 1979, and I saw it in 1980, and I was just turned 5 years old at the time. As I grew up, the Space Shuttle was a symbol of the American space program run by NASA, National Aeronautics and Space Administration. But in 1986, on the 28th of January, I was 9.5 years old, and I watched the TV footage of Challenger exploding and burning up during its ascent. And I still remember that just sheer shock and disbelief that it could actually have happened. The 7-member crew were killed. It's amazing the impression that it makes on you. It still does, even today, watching that footage again and again and again. And this year marks the 30th anniversary of the disaster, only 7 weeks ago as I record this, in fact. The thing to keep in mind about the Space Shuttle is that it was an expensive, complex, and truly amazing piece of technology. It was the embodiment of an idea that you could make access to space cheaper if you had reusable rocket technology. And it sort of seems to make sense in theory. We build rockets that launch once, fly once, and then they either burn up or land in the ocean, most of which we don't retrieve. The problem is that it didn't really work out that way with the technology they were using at the time. The idea of launching like a rocket and then landing like a glider, I think it captured people's imaginations because it was similar to a plane, and well, planes are, pretty cheap to run these days. So, yes, unfortunately, the simpler crew modules that splashes down, relatively unguided, a couple of drag chutes, and it's retrieved from the ocean, seems to have proven itself to be more reliable and has certainly simpler design in the long run. Of course, there's newer ideas like Spaceship Two that lands like a shuttlecock to slow it down, and there's a vertical takeoff, vertical landing approach that SpaceX are using for the Falcon 9 rockets. But each of these methods have their own risks, and whilst they also promise to reduce the cost of access to space, so did the Space Shuttle at the time. But to understand exactly what went wrong with Challenger, we need to understand the basic components of a space shuttle. Or at the time, actually, it was referred to as a Space Transportation System, or STS. The program was called that. And every launch was numbered STS- and then a number of the mission. All the launches for the space shuttle took place at the only place in the world that was actually designed to handle them, and that was the Kennedy Space Center in Florida, in the United States of America. So let's talk about the components of a space shuttle. Space shuttle itself was born from a proposal, or maybe considered a recommendation, from the report from the Space Task Group saying that a reusable, chemically fueled shuttle operating between the surface of the Earth and low Earth orbit in an airline-type mode. And that report was released in the late 60s, I think it was. The orbiter itself, the space shuttle that people think of, the glider, the crew and cabin area, as well as the cargo bay with the engines on it, that was referred to as the orbiter. And the orbiter had 3 primary engines. They were Rocketdyne Block 2s, and the nickname, the abbreviation was SSMEs, which rather unhelpfully simply is described as Space Shuttle Main Engines. So they were specially designed for the space shuttle. And here are the figures that combined those 3 primary engines produced a total of 1,181,400 foot-pounds of thrust, which is 5.255 meganewtons. That's meganewtons of liftoff thrust at sea level. Since, of course, thrust varies based on atmospheric pressure, and they were powered by liquid oxygen and liquid hydrogen fuel. The length of the orbiter itself was 122 feet or 37 meters long. It had a wingspan of 78 feet or 23.8 meters, and it was about 56.5 feet high, which is about 17 meters high. Now, during the design and the development of the Space Shuttle orbiter, they found that the quantity of fuel that they would need to lift that final weight of the Space Shuttle orbiter with its payload and everything else, and the weight of the orbiter on its own, by the way, was 172,000 pounds or 78 tons. So they're going to need a little bit more kick because they had no space to store the fuel. Hence, they added a very large external fuel tank, and that would hold the fuel. And of course, when that detached after launch, it would make the overall orbiter lighter. Now, the length of the external tank was nearly 47 meters long. That's 154 feet. And it was about 8.5 meters in diameter, or 27.5 feet in diameter. And it, in terms of propellant, the volume that it could store was 2,025 cubic meters, or nearly 535,000 US gallons. So a fair bit of liquid oxygen and liquid hydrogen in there. Now, all this added more weight, again, because the fuel itself has mass before it burns, hence the liftoff weight of any rocket is the heaviest as it's about to lift off. And because of this additional weight, they then needed to add a further 2 items. They needed to add 2 solid rocket fuel boosters on each side of the fuel tank. Now, the solid rocket boosters only burned for 124 seconds, but they accounted for 83% of the liftoff thrust. So it's quite significant. Now, after they'd completed their burn, then they were jettisoned around about 46 kilometers in altitude. A parachute opened up, and they would then splash down harmlessly enough in the ocean to be recovered and reused another launch. Each of the solid rocket boosters were about 45.5 meters long, which is 150 feet, and 3.7 meters, or 12 feet, in diameter. Now, the empty weight of those solid rocket boosters was 68 tons, or 150,000 pounds. The external tank, as I said before, also detaches and jettisons, but they didn't recover it. They had their reasons, I suppose, and they didn't leave it in orbit, although theoretically it could have been. There were several proposals actually to keep those in orbit and use them as materials for constructing an orbiting structure of some kind, but they never followed through with it. The launch profile, or sequence of events if you'd prefer, for a space shuttle launch approximately follows like this, or at least these are the key points. It's quite a bit simplified, of course, but these are the key points, at least in my mind. Fuel from the external tank begins to pump into the orbiter. Hydrogen igniters spray what are essentially sparks underneath the engines, and that ignites any stray hydrogen. And then the main engines themselves ignite. They ignite in a sequence. They don't happen simultaneously. There's 120 milliseconds of stagger between the 3. After they've confirmed to have started, the 4 nuts hold down each of the solid rocket boosters to the pad. So there's 8 in total. And these have very, very small detonators on them. So they are those 8 nuts are detonated. And this releases the solid rocket boosters at the moment that they are themselves fired. And they're obviously launching with maximum thrust. 30 seconds into the ascent, the main engines on the space shuttle, SSMEs, they're throttled back to about 70% of capacity. And the SRBs are also designed to experience a drop in power to about 70% of their maximum at approximately 50 seconds from launch to ensure that the shuttle is a very important moment, that it does not exceed its structural limitations. And that's the point that they refer to as maximum Q, or max Q for short. And Q is technically, it's referred to as the aerodynamic pressure, the dynamic aerodynamic pressure exerted on the vehicle. And that's the point at which The speed of the shuttle is so great, but there is still enough drag from the atmosphere that is pushing through at that point as to cause the maximum structural strain on the entire assembly. And it's considered by aeronautics engineers to be the second most dangerous part of a launch sequence, and it's second only to initial liftoff. At 124 seconds into the ascent, as I said previously, the solid rocket booster's fuel is consumed, and 2 seconds later, pyrotechnic fasteners that attach them to the main tank are detonated, and that releases the solid rocket boosters from the external tank, and then some very small separator rockets, or thrusters if you'd prefer, push the solid rocket boosters away laterally from the side of the tank and the orbiter so that they clear them safely. At about 8 minutes and 30 seconds after launch, the main engines will cut off, and shortly afterward, the external tank will also detach, and then it burns up on re-entry. Only very small fragments will make it back to Earth and would either land in the Pacific or Indian Oceans, depending upon the launch trajectory. And at least, well, that's what's supposed to happen. And it had done, actually, for all 24 missions that preceded Challenger's final flight. In fact, Challenger itself had flown 9 times successfully out of those 24 without significant incident. So what went wrong this time? STS-51L, the flight number. The hype behind the 25th shuttle mission was more about the people on board it than anything else specifically. It was the first ever shuttle mission that had a non-government civilian on board, a schoolteacher, Krista McAuliffe, and she'd been selected after a very long process out of 11,500 applicants. 2 decades of budget cuts and a distinct loss of public interest were key pressures for this specific launch. At this point, the Apollo days were far, far behind them, and NASA wanted to capture the public interest and show that anyone, albeit with 5 months of training beforehand, could reach for the stars. And why not, right? I mean, you could be an astronaut. The flight itself had already been delayed a week for a myriad of reasons. It was actually originally supposed to launch on the 22nd of January, but the previous mission from earlier in the month had pushed this back. At first it was the 23rd and then very quickly slipped to the 24th. Unfortunately, bad weather at the abort landing site in Dakar, Senegal, on the 24th pushed it to the 25th. NASA briefly kicked around the idea of using Casablanca as an abort landing site later that day. Instead, unfortunately, it would have been night in Casablanca at that point, and they had no night landing capability. So the launch was pushed to the 26th. But then the weather at the Kennedy Space Center was predicted to be unacceptable, so it was pushed to the 27th at 9:37 a.m. Eastern Standard Time. But then they had problems with an exterior access hatch. There was supposedly there was a series of microswitches that indicated that the access hatch was locked closed, and one of them was malfunctioning, and it was not reporting that it was shut, and hence it was a critical interlock. Once they'd rectified that, a stripped bolt prevented them from removing a closing fixture on the orbiter. Once they'd fixed all that, they missed the launch window that day. So now the launch was set for between 9:38 a.m. and 12:38 p.m. Eastern Time on the 28th of February as a primary launch window. The delay now had been a week. The morning of the flight, the weather was unseasonably cold, and overnight a layer of ice 7.5 centimeters or 3 inches thick and a meter long or about 3 foot long icicles were hanging from parts underneath the space shuttle. No space shuttle had ever launched in such cold conditions. The launch control decided that they would delay the launch time by 2 hours. That would give them time to clear whatever ice they could and let the colder conditions warm up, thawing ice, in hopes that the weather would warm up some more. The air temperature at the time of launch, that was 11:38 a.m., so nearly midday Eastern Standard Time, was 2 degrees Celsius. That's 36 degrees Fahrenheit. And now that was 15 degrees colder than any previous launch. And this is Florida. So yeah, it was cold. Melbourne, Florida, located 35 miles from Cape Canaveral, recorded a low temperature of 26 degrees, noting that the normal low on January 28th is 50 degrees. Now, Orlando also had a record low of 26 degrees that day, and both of those records still stand today. So yeah, it was very cold, uncharacteristically cold, no question. 9 minutes before liftoff, all of the pre-flight checks passed without any issues. In the history of the USA's spaceflight program, at that time, no astronaut had ever died during liftoff. At approximately 10 kilometers of altitude, the shuttle hit a severe crosswind during launch, which was unusual, but the control system compensated. At 66 seconds, as it passed max Q successfully, the engines returned to full throttle. They refer to that as throttle up. However, 73 seconds after launch, the entire orbiter and external tank exploded in an enormous fireball. The two solid rocket boosters were separate now, and they flew away, only to be remotely detonated by the ground control moments later. As pieces of the debris fell back to Earth, NASA officials observed that the crew compartment appeared to have separated from the orbiter. They tracked its trajectory back to Earth and scrambled rescue personnel to its predicted location. But without any fall arrest system or parachutes as part of that module, they estimated it impacted the ocean at 320 kilometers per hour. Had the crew somehow survived that explosion, they would have no chance of surviving an impact at those speeds. None at all. STS-51L's investigation was a presidential commission. They spent 5 months investigating recovered wreckage and the details leading up to the crash. The right solid rocket booster had malfunctioned. Each solid rocket booster is made up of 4 distinct sections. They are all bolted together. Where the sections join, it's referred to as a field joint, and the joint itself is sealed by 2 O-rings. Think of it as 2 cylinders, one that has an end flange that is slightly smaller than the other, and they fit, one fits inside the other, and there are 2 O-rings that run the circumference of where they join, and they are pressed against each other, and they are held in place under a large amount of pressure. The O-rings themselves are made from rubber, which is an interesting choice. When the solid rocket boosters are lit, they can't be shut down. Unfortunately, that's the nature of solid rocket fuel. When they light, they burn from the inside outwards, and the hot exhaust gases push equally on all sides of the internal walls of the rocket cylinder, but with only one exit point as designed, the exhaust, this creates the thrust to propel it upwards. There you go, you have a rocket. The problem with a multi-segment design, though, despite the fact that it was easier, cheaper, quicker to construct accurately, the segment joints would expand and flex as fuel was consumed and under different flight stresses. And these expansions and contractions would happen multiple times every few milliseconds, and the O-rings were designed to expand and contract to prevent any hot exhaust gases from escaping. The problem is that even if a slight amount escapes, because the seal isn't complete, it blows by in the gap. That then creates a weak spot. That weak spot erodes as more gas passes by, which further erodes, making the gap wider until the gas can then escape pretty much unchecked. The lowermost field joint on the right side's booster did not expand adequately enough to seal the joint under the launch stresses. This is because rubber has a fundamental flaw. At low temperatures, rubber becomes rigid and it isn't pliable. The O-ring rubber used on the Challenger's SRBs was tested and found not to provide the correct seal performance below 12 degrees Celsius or 54 degrees Fahrenheit, and the launch conditions were far, far below that. During the initial stages of the launch, the right solid rocket booster was venting exhaust gas directly onto the support, connecting the lower part of the right solid rocket booster to the external tank. By comparing the multiple angles of video taken, the commission calculated the smoke at liftoff came from a 1.3 meter section of the right solid rocket booster's surface, 13 meters up. It billowed upwards. It was black smoke, which is indicative of rubber burning. There were 9 distinct large puffs of smoke from that location for approximately 2 seconds. But then they disappeared. At the moment the solid rocket boosters ignite, they also blow the lockdown bolts. Now the process, this process of releasing from the platform results in extreme vibration and a rocking motion as the shuttle tilt angle adjusts to being free-floating, near vertical, and no longer connected to the ground. The vibrations and their resonant frequency creates a phenomenon that NASA engineers have referred to as twang. Careful examination of those smoke puffs showed that they aligned near perfectly with the twang frequency at launch. There should have been a continued leak and then an explosion within seconds of that leak. But interestingly, it sealed itself. For the longest time, investigators weren't sure why. A subsequent theory that was proposed was that the only material that could possibly reseal a damaged O-ring from those solid rocket boosters was actually the aluminium, which was used to increase the thrust in the solid rocket boosters' rocket fuel. Aluminium, of course, would leave a trail of molten metal slag. Aluminium, bits of molten aluminium. That's a byproduct of ignition. So if you were to stand underneath a solid rocket booster when it was taking off and not get burnt to death, of course, then you would get showered by metal slag of aluminium pellets. Anyhow, in this case, the slag sealed the breach in the O-rings, and the launch, quite surprisingly, continued successfully, more than by luck than anything else. However, that failure was dormant for the time being. When the attachment gave way after 73 seconds, the entire bottom section of the external tank fell apart. That dumped most of the liquid hydrogen and oxygen in an instant. And at that same time, the right solid rocket booster twisted inward and impacted the top of the external tank. And 200 cameras were shooting the footage of the launch, and they were the primary tool in determining these conclusions. So everything was going well until 59 seconds the flame became visible on the right side of the right SRB, same spot where the smoke had come from at the moment of launch. 2,000 transmitters covered most parts of that orbiter and the external tanks and solid rocket boosters. And the telemetry from those transmitters, there's a pressure transmitter monitoring the pressure in the solid rocket booster on the right, and it dropped at 60 seconds. It dropped 24 psi just in a matter of milliseconds. Clearly there was a leak. A leak had happened at that moment. The crosswind that I mentioned earlier, that Challenger crossed at that time, was obvious. All you had to do was look at the cloud trail from the exhaust. It literally did a 90-degree right-hand correction as it went through that layer of high-speed air. It was in fact so severe that it required a 2-degree thrust angle adjustment of the nozzles in order to keep the shuttle on trajectory. I mean, that's fine. That's what the control system was designed to do. And it worked perfectly. And that crosswind and then the intensity of that crosswind was picked up by a lateral accelerometer. Now, 30 minutes prior to the launch, it was found later that it was measured at approximately 300 kilometers per hour headwind. And that was experienced by a commercial passenger flight passing through the same section of airspace near the Kennedy Space Center. The force of that crosswind and hitting it at that speed at max Q shook the SRB so violently that any slag that had been resealing those O-rings, it shook loose and began leaking immediately. And this time, the leak was going to be terminal. Every astronaut has an air supply line fitted to their helmet for use in case of an emergency. During the recovery, they found that 3 of them had been activated, which meant that at least 3 of the astronauts survived the explosion. They may not have been conscious, but there was a very good chance that they were alive for the 2.5-minute fall back to Earth, but we don't know for sure. and never will. So now that we know what went wrong, at least from a mechanical point of view, what actually went wrong? What caused this to happen? Because they say it's not rocket science. Well, this is rocket science. And the people doing it are very smart. And they try to stop it. It turns out that a group of engineers, they worked at a company called Thiokol, and its full name is MTI, Morton Thiokol Incorporated. Roger Boisjoly worked for Thiokol, and he claimed that evidence from a prior launch, it was in 1985, it was a launch of another space shuttle, Discovery, it lifted off at 11 degrees Celsius. Now, when they recovered the boosters after that launch, they found a large amount of soot and scorching around the field joints, with only 1 millimeter of rubber remaining before they would have burned through completely. Roger had seen the weather report for the latest launch on the 28th and spent most of his afternoon, starting at about 1 in the afternoon, trying to convince engineering managers that there would be a problem launching in such low temperatures based on his knowledge of engineering, physics, and the prior evidence from 1985's launch. He had been trying to organize detailed test data to generate temperature-related statistics on these O-rings for many months leading up to that day. However, management did not see the value in that testing since the rings had been functioning perfectly well so far, and that funding to do those statistical tests was needed elsewhere at MTI, because budgets were tight at that point. It culminated in a teleconference call starting at 7 p.m. on the 27th of January 1986. That was the day before, the evening before. MTI had 4 engineers present at that meeting: Roger Boisjoly, Arnie Thompson, Bob Ebeling, and Brian Russell. MTI also had 4 executives at the meeting: Vice President of Engineering Bob Lund, Senior Vice President Jerry Mason, Vice President and Program Manager Joe Kilminster, and Vice President Cal Wiggins. Now, in addition to this, there was a large number of managers from NASA at the Kennedy Space Center, and the NASA head of rocket boosters, Lawrence, also referred to as Larry, Malloy, from Tennessee, was also on the line. Thiokol's managers initially recommended to NASA that they play it safe and not launch on the basis of Roger's evidence that he had presented. Malloy knew full well that Roger didn't have any statistical evidence to back up his claims, only the photographic evidence, and kept pushing Roger for it, asking him, "Can you give us actual calculation numbers concerning the probability of failure?" After being probed several times, Roger snapped back, saying, "You know very well I can't get you those numbers because Arnie and I have been trying to get resiliency data since last October." Unfortunately, that outburst and the insinuation that MTI hadn't done their due diligence in engineering, although it was true, was definitely overstepping a line in front of a client being NASA. So SVP Jerry Mason was so unimpressed with the comment that Roger had made, the whole character of the phone conference shifted. Malloy put Kilminster on the spot for his launch recommendation, to which Kilminster replied, "Based on the engineering information that was just presented, I do not recommend launching Challenger tomorrow." He said he did not recommend. Wanted to be clear that he said he did not. Larry Malloy was then alleged to have said, "My God, Thiokol, when do you want me to launch? Next April. Why are you guys coming up with launch commit criteria on the eve of a launch?" When Malloy had responded so angrily, Mason requested MTI put the call on hold for 5 minutes. It actually ended up being more like half an hour, as the MTI reconsidered their position amongst their own staff. Mason opened with, "We need to make a management decision." Boisjoly screamed at his managers to look at the photographic evidence from the launch once again from the previous year, at which point Jerry Mason spoke in a quiet voice to Boisjoly, "Take off your engineer's hat and put on your management hat." Man, I've heard that one. MTI and NASA were at the beginning stages of negotiations. They were worth $1 billion. And that was to build, well, oddly, rocket boosters into the next century. So MTI could not afford any setbacks. Funding was already tight at MTI, and the failure of management in preceding months to allow detailed statistical testing on the O-rings had undermined their case. And the teleconference resumed. By 8:30 p.m., the decision had been made, and the fate of Challenger had been sealed in the process. I did some digging back through the historical weather records for that zip code. Had NASA pushed the launch back 48 hours, the temperatures would have been 22 degrees Fahrenheit or 12 degrees Celsius warmer, which had there been a launch window at the same time of morning, they would have launched without incident. So there are ultimately two failures in the Challenger disaster. And it wasn't specifically the O-rings. It was a failure of the lack of definition around go, no-go criteria for launching. There was no go, no-go criteria for ambient temperature. Second of all, the financial pressures influenced a safety decision. MTI had not done due diligence in investigating and gathering the test trial data that they needed to ultimately prove the limitations of their O-ring design over temperature. Now, people will say that it's not Roger Boisjoly's fault. He tried to secure the funding, but ultimately MTI management structure did not understand the risks well enough, or it wasn't pushed hard enough. Pick one. Maybe it was both. But ultimately, the big one were the financial pressures affecting safety decisions. It's a horrible thought because people start to think, well, how much is someone's life worth? How much is risk worth taking? People will explain away risk like it's okay and start negotiating and thinking, well, how much is someone's life worth? And to be brutal for a moment, I've heard people sort of say, well, you know, it's risky doing insert task name here, and people know the risks. And sometimes I think, well, there are 7 billion people in the world today. But the thing is, someone's life is still priceless. And in my own mind, to address that, I like to steal an idea from an episode of, and I'll geek out a bit here, Star Trek, The Next Generation, Time's Arrow Part 1, if I may, and I'll just paraphrase it slightly. The point is, one person becomes a trivial creation, a single one amongst countless others. But the counterpoint is, a diamond is still a diamond, and even if it is one amongst billions, it still glitters as beautifully. If there's ever a question of money versus life, there is no question. There can be no question. Choose life. Choose the safe option. Money be damned. It's only money. NASA and MTI managers were blamed for the accident and their poor decision to proceed with the launch in the face of evidence suggesting a further delay was warranted. They paid $4.6 million in compensation to the astronauts' families, MTI did. However, a $1.8 billion contract was awarded to MTI after the disaster to develop new solid rocket booster technology. Malloy was offered a promotion to the head of development for all propulsion systems. Roger and Bob, the engineers who were trying to stop the launch, shortly after the disaster both resigned, and Roger suffered an extreme nervous breakdown. Shuttles were grounded for nearly 3 years while the investigation continued and redesigns and retrofits occurred. What's terrible for me is the engineers that tried to stop the launch, like Roger Boisjoly and Bob Ebeling, suffered from depression for many years, carrying guilt about what had happened, blaming themselves, not pushing the case harder. They should have pushed it harder. That's what they would say. And in this case, would it have ever made a difference? and I guess we'll never know. A recent interview with Bob Ebling on NPR prompted many letters of support from listeners saying he'd done nothing wrong. And at 89 years old now, Bob had his daughter read them to him because his eyesight's going. And it helped him deal with that guilt that he's carried for 30 years. Whether guilt's justified or not, it's an emotion. So, like all emotions, it is justified to have it. I wonder, though, how many people that pushed to launch resigned from engineering practice, or at least NASA and MTI following the disaster. Yeah, if you ever have to make a decision to go ahead and put people's lives at risk, or to delay, investigate, and be safe, I'd suggest you think about this. No one will thank you if it works perfectly, or if they do, it'll be fleeting. Even if it results in a delay, but if it breaks, you'll be the one that has to live with the consequences. And if you're sure, you're absolutely sure, then don't let anyone or anything change your mind or shout you down. Stand your ground. Stand up to those that don't listen. No one else will thank you. But someday you will thank yourself. If you're enjoying Causality and want to support the show, the best way is becoming a patron via Patreon. It's at patreon.com/John Chidgey. So if you'd like to contribute something, anything at all, it's all very much appreciated. This was Causality. I'm John Chidgey. Thanks for listening.